Swayam Prabha. Digital India. Educated India.
In this lecture, we will complete our discussion on panel method and subsequently we will discuss about the vortex lattice method. Let us recollect where we completed in the last lecture regarding panel method. We discussed about the lifting and non-lifting flow past airfoils, how we can solve them using panel method. In that context, we had discussed about the vortex based panel method as well as source sink based panel methods. And you may recall that the boundary surface was discretized into panels which were like straight segments, and at the central location of each such panel we had located a control point, and subsequently we solved for the strength of the singularity at that control point. So, when it was a point vortex based panel method, then it was the strength of the vortex which was solved at this control point. Now, there are certain limitations of this approach which can be better addressed by using higher order panel methods. So, let us very quickly discuss about one or two limitations what the approach has. For example, the solution is sensitive to the number of panels that you use. If you use too few a number of panels, then the solution could be quite erroneous, and it also depends on the size distribution of the panels. If there are certain panels which are extremely large, that means very large lengths of the panels are involved, then usually the accuracy will degrade quite a bit. And then additionally, for the vortex based panel technique, you remember that we removed one of the discretized equations arbitrarily. Depending on this arbitrariness, the solution can become quite erroneous again, depending on which particular equation we are removing. So, for one of the control points, we had removed the equation in order to accommodate the Kutta condition. Otherwise, the difficulty was that the system was overdetermined. So, in order to accommodate the Kutta condition, we were removing one equation, and that was bringing in the arbitrariness and also could produce errors. One of the ways of removing or reducing these errors, as we mentioned earlier, is using higher order panel methods. And what do we do in such panel methods? Instead of defining the unknowns at the panel centers, we try to work with the strength of the singularities at the end points of each panel and make the distribution vary linearly in between or quadratically in between. So, usually the accuracy is improved. So, when you linearly interpolate, you are using a second order accurate panel method. So, this is more or less where we end the panel method, the panel technique, and now we move on to discuss a technique which will help us to solve potential flow past 3-dimensional wings. We will discuss about the vortex lattice method. So, we have learnt about the lifting line theory, and we remember that it works pretty well for slender wings. So, when we are talking about especially about straight slender wings, where the aircrafts are using high aspect ratio straight wings of this kind, then it is a very good idea to use the lifting line theory, because the model very well fits the plan form, and therefore, the predictions will come out to be pretty good. However, if you have low aspect ratio wings, and which could also be swept or delta wings apart from straight tapered wings, it is a better idea to bring in a more advanced model, because the predictions improve that way. And the numerical technique which we deploy for solving such problems is what is called as vortex lattice method or vortex lattice technique. So, let us make a simple sketch to explain how we do the numerical modeling. Let us take a wing platform like this, and then let us draw a couple of lifting lines followed by trailing vortices. So, on arbitrary planforms, you need to do more than what lifting line theory will do for you, and this takes us close to what is called as the lifting surface theory, where we try to use a large number of horseshoe vortices to span the entire wing planform. In doing so, let us try to identify what these vortex filaments are doing, for which we take vortex filaments along the two orthogonal directions. It will be convenient if we fix the axis system at the center of the wing, let this be the x direction, the other one the y direction, and we will define vortex filament strengths gamma along the y direction, and let us say delta along the x direction, and additionally we will also define the vortex filaments in the wake. We will see soon that gamma and delta are functions of x and y, while the delta w will be purely a function of y only. So, let us try to argue why it is like that. Let us call this as the lifting surface. This is the wake. So, if we look at the vortex filaments which are parallel to the y axis, so these are nothing but lifting lines placed at different chordwise stations and they are obviously parallel to the y axis. So, there is a vortex sheet formed by these lifting lines. Let us define the strength. So, the strength of this sheet is given by gamma per unit length along x axis. Now, by definition gamma varies along y, analogous to the variation of the capital gamma for a lifting line. Additionally, it also varies along x because you are moving from one lifting line to the other, and the strength of each lifting line may be different from the other. Therefore, in general gamma is a function of x and y. In a similar manner, we can define the other family which are parallel to the x. So, the other family comprises of what? They comprise of the trailing vortices. Which are parallel to the x axis, and you can put similar arguments to say that they are function of x and y, and the strength delta is per unit length along y axis. So, this is how we define the vortex sheets formed by the lifting lines and by the trailing vortices, giving you the gamma and delta distribution. We say that gamma xy gives us the span-wise vortex strength distribution, and the delta xy gives us the chord-wise vortex strength distribution. As far as the wake part is concerned, the delta w is purely a function of y, because the trailing vortices do not meet any vortex filaments once they leave the trailing edge. Additionally, the strength with which they leave the trailing edge remains unchanged. So, strength at the trailing edge of the wing is what will be the delta w at a given y. So, keeping these ideas in mind, let us take this forward, so that we can finally figure out what is the sum total effect of the span wise and chord wise vortex sheet distribution as well as the wake vortices on the downwash induced at a particular point on the wing planform. Why we are aiming for that is, once we work out this downwash, we will find out what will be the upwash due to the free stream, and then we would equate them to 0. That means, the sum of the upwash and the downwash, once we equate it to 0, that will ensure that the wing surface becomes a streamline of the flow. So, in essence what we are trying to say is that the wing is pitched at some angle of attack with respect to the free stream, and in that situation the flow is moving smoothly past the wing, remaining attached, and in the process the wing is generating some lift. So, we are trying to model that. So, we will make another drawing which makes the picture a little clearer in terms of the mathematics. So, we are once again drawing a part of that wing with a closer view of the details. So, if you take a small element, on that small element we are going to locate the vortex filaments parallel to x and y directions, and we will assign some dimensions here to that elemental region. Let us call this as d eta, let us call this as d xi. Let us mark this point as, say, xi eta. This is of course 0 0, and you remember that we will have a gamma d xi and delta d eta strength filaments acting through that xi eta point. Further, we mark the angle theta, which the vector connecting the point xi eta and x y makes with the y axis. So, based on these details, you can work out what will be the total downwash at the field point x y using the Biot-Savart law. Remember that the entire gamma as well as delta vortex sheets are going to create the influence. So, this is the downwash which will be produced by the gamma and the delta fields. This should be delta. And then comes the effect of the wake. So, this is on the surface of the wing, the other part comes from the wake. So, you can try working out this relation on your own by using Biot-Savart law. We are just stating the final relation, okay? And we are going to use a nomenclature here, let us say W I induced by the gamma, delta and delta W vortex sheets. That is the induced velocity at that point P, and then what we are trying to say is that that width the W coming from the free stream should be equate to 0 to make the wing a streamline of the flow. The interesting part is that if you try to work out this problem using some numerical technique, then you will find that these trailing vortices which move into the wake, they would even roll up like this, they might even curl. So, let us take this mathematical formulation forward in order to accommodate the vortex lattice numerical method, which can help us come up with a numerical solution of this formulation. So, in order to do that, what is essentially done is that on the wing we try to create panels. Now, these are of course planar panels, they are not straight lines like we discussed in panel method, because panel method was applicable for a 2D situation, while here it is a 3D surface. So, you create a planar panel and then you define a horseshoe vortex with certain geometrical details which you have to ensure. Once you have created the panel, let the panel have a certain length, let us say Lx and Ly. So, it is important that you follow the convention that you locate the lifting line at Lx by 4 from the leading edge of the panel, and then you define a control point at 3/4 chord of the panel. So, let this be the control point. So, this is the point where you are going to numerically impose this condition, and that will be applied at each and every panel that you are creating. So, as we said that this will be located at 3/4 Lx from the leading edge of the panel. So, this gives you one of the horseshoe vortices, and of course, this will have a certain strength which has to be worked out. Now, if you have n number of control points at which the above equation has to be satisfied, then you will end up solving n number of horseshoe vortex strengths. By having discrete forms of these equations applied. So, finally, when you have the entire wing, then there will be a kind of a lattice structure of horseshoe vortices which will be visible to you. That is why we name the method as vortex lattice method. So, this is the way you would end up discretizing the entire plan form. For simplicity, we are showing it on a rectangular plan form, but it works for arbitrary plan forms essentially. And then you have the control points located on each one of the panels as we discussed few minutes back, and what we are essentially doing is we are applying the discrete form of this equation at each one of those control points and thereby solving for the unknown horseshoe vortex strengths. So, this is basically the essence of the vortex lattice method. So, in this lecture we completed our discussion on panel method and we subsequently discussed about fundamentals of vortex lattice model for numerical solution of flow past finite wings. Thank you.